Welcome students once again into the class of number theory, and in this video we will have some definitions of a different kind of arithmetic function, that is greatest integer function, and its applications, and especially the Polygonal formula. So we are starting with the definition of greatest integer function. So let us see what is greatest integer function. Basically it is a greatest integer function. F of x is denoted as box x. And what is box x? We define it as for every real number x, there exists a unique integer. There exists a unique integer box x such that x minus 1 is less than or equal to box x is less than, here you should have less than or equal to. So this is the definition of, suppose your x is 5.7, so 5.7 is here, 4.7 is here, and there is a unique integer here. What that integer is? That is 5. So that means box of 5.7 is 5. If you take x to be an integer, suppose you take x to be 6, then it is 6 here, it is 5 here, and there is a unique integer once again, and this is 6. So box of 6 is 6. In fact, for every real number x can be expressed as box x plus round bracket x, where box x is the integral part and this is the fractional part. So fractional part, this round bracket x, it is lying between 0 and 1. It may be equal to 0, but it is strictly less than 1. It cannot be equal to 1. So this is your greatest integer function and this is your fractional part function. So two functions simultaneously, greatest integer function denoted by box x and fractional part function that is denoted by round bracket x. So these are the two functions, but we are here concerned with only greatest integer function. So it is the definition, and after definition we will have some theorems, some results, some questions regarding greatest integer function, and especially the Polygonal formula, which is very important. So before moving on to the de Polygonal formula, I am going to have a very easy theorem. So see what the theorem is. It is very easy, very short theorem you can say. Let n and a be positive integers. Let n and a be positive integers, then number of integers, in fact positive integers, the number of integers among 1, 2, 3 and so on up to n divisible by a is equal to the greatest integer function of n by a. This we are to prove. This is the very first theorem regarding greatest integer function. So what we are to see here, if you consider these numbers 1, 2, 3, 4, 5 up to n, and a is any positive integer, then how many multiples of a will be here? How many multiples of a will be here? The number of multiples of a will be box of n by a. So let us see how to prove it. Let multiples of a let multiples of a among 1, 2, 3 and so on n be. Now multiples of a be definitely of the type a, 2a, 3a, and let the last multiple here in among these numbers be ma. So one thing is clear, that the largest multiple of a here, ma, it is definitely less than n. It is definitely less than n. So ma is less than n, and it is on the other side is less than n and is less than m plus 1 a, and it may be equal to, because this ma may be equal to n. And now multiply this inequality throughout by 1 by a. Since a is a positive integer, 1 upon a is a positive real number, you can say, and multiplying by a positive real number will not change the sign of the inequality. So what you are going to get from here is that m is less than or equal to n upon a is less than m plus 1. And by the definition of now greatest integer function, this n by a greatest integer is equal to m, from the definition of greatest integer function. So what is m? M is the number of multiples of a. M is the number of multiples of a. So the number of multiples of a among these integers is equal to box n by a, and that is what we wanted to prove. So this is very small theorem, very easy theorem, you can say. And then we move on to the main theorem that I'm talking about for last 2 or 3 videos, that is deep Polygonal formula. What is deep Polygonal formula? First of all, so it is the statement of the theorem, the Polygonal's formula. First of all, we write the statement and then we will move on to the proof. Let P be a prime number. Let P be a prime number, and let n be a positive integer. A positive integer if p raised to the power e max divides n factorial. Max divides n factorial, I have told you earlier also that p power e max divides n factorial means p power e divides n factorial, but p raised to the power e plus 1 does not divide n factorial. So that means p power e max divides n factorial. So if p power e max divides n factorial, then this e is equal to sigma I vary from 1 to infinity n upon p power I. Here we have mentioned I vary from 1 to infinity. So it looks that it will contain infinitely many terms, but it is not, because whatever n is, whatever p is, at some stage p power I will become greater than n, and after that all the terms of this sequence will become 0. So we will have only finite number of terms in this summation. Okay. So first of all, let us have an application of this, then we will move on to the proof. Suppose I ask you a question. 7 raised to the power e max divides 300 factorial. That means 7 power e divides 300 factorial, but 7 raised to the power e plus 1 does not. What is the value of e? That means how many maximum power of 7 can divide 300 factorial? From this formula, this e will be equal to sigma I vary from 1 to infinity, and then you will get n. N is here 300. 300 divided by 7 raised to the power I. And now put here the values of I is equal to 1, 2, 3, 4 and so on. What we are going to get is box of 300 upon 7 plus box of 300 upon 7 square plus box of 300 over 7 cube plus and so on. Now 300 divided by 7. What it is equal to? If you divide 300 by 7, you will get 42 point something. And 42 point something, its greatest integer, that means its integral part is 42. So it is 42 plus. Similarly, here you divide, it will become 6 point something. 6 point something means integral part is 6. Then in the next it is 343. So you will get 0 point something. And 0 point something means the integral part is 0. And after that each of the term will become 0. That's what I was telling you, that this sum is not the sum of infinite terms. At some stage it will become 0, and after that all the terms will be 0. So you will have only finite number of terms here. So it is 48. That means 7 raised to the power 48 divides 300 factorial, but 7 raised to the power 49 does not divide 300 factorial. That means 748 max divides 300 factorial. This is what is being told by this theorem that is known as the Polygonal Formula, which we are going to prove in this video. So next time I will prove this this theorem, and then we will have another 1 or 2 more applications of this theorem. So let us see what to do to prove this theorem. Proof. We will prove this theorem, this de Polygonal formula, with the help of principles of mathematical induction. We will show that the result is true for n is equal to 1, and then we will suppose that the result is true for n minus 1, and then we will show that the result is also true for n, and by principles of mathematical induction it will prove that the result is true for all natural numbers n. So what is happening if your e is 1? Let p be any prime number. Let p be any prime number. So p raised to the power e max divides 1 factorial. That means p raised to the power e max divides 1. Here clearly your e is 0, because p raised to the power 0 divides, that means 1 divides 1, but p raised to the power 1, that means the prime number p does not divide 1. So e is clearly 0. From this result, what you are going to get now? Sigma. Here your n is now 1. 1 upon p raised to the power I is, I vary from 1 to infinity, and when you will expand it, you will get 1 upon p plus 1 upon p square plus and so on. And right from the first term, you will get 0, because 1 upon prime number is 0 point something. 0 point something means its integral part is 0, and then after this 0, each term will become 0. So your right hand side is also 0. Left hand side e is 0, right hand side is also 0. That means the result is true for n is equal to 1. Now we suppose that the result is true for n minus 1. So we have proved the first step of the principles of mathematical induction, that is the result is true for n is equal to 0. Suppose the result is true for n minus 1. That means if p power k max divides n minus 1 factorial, then your k is sigma I vary from 1 to infinity n minus 1 upon p raised to the power I. This is true. This is the second step of the principles of mathematical induction, that the result is true for n minus 1, and if the result is true for n minus 1, that means if p power k max divides n minus 1 factorial, then k will be given by this formula, sigma I vary from 1 to infinity n minus 1 upon p raised to the power I greatest integer. This is we have supposed to be true. Now we will move on to the final step, that means we will prove that the result is also true for n. For that, let p raised to the power j max divides n. I am not having here n factorial, only n. Let p power j max divides n. This means p power k max divides this term, p power j max divides n. So their product p power k into p power j max divides this product n minus 1 factorial into n. That means p raised to the power k plus j max divides n factorial. N into n minus 1 factorial is n factorial. What we want to prove now? Actually, our theorem says that if p raised to the power something max divides n factorial, then this something should be equal to sigma I vary from 1 to infinity n upon p power I greatest integer function. So here this k plus j must be equal to that. So that means we are to now prove that this k plus j is equal to sigma n upon p raised to the power I vary from 1 to infinity. Actually we are to prove now this result, or you can say taking this k to the other side, or you are to prove that j is equal to sigma I vary from 1 to infinity greatest integer n upon p raised to the power I minus k. But you are having the value of k. So substitute the value of k from here to here. So what you are to prove? You are to prove that j is sigma I vary from 1 to infinity greatest integer n upon p raised to the power I minus sigma I vary from 1 to infinity greatest integer n minus 1 upon p power I. That means you are to prove this. Further, it can further be solved by combining these two summations. Sigma can be taken as common and these two will be collected together. So in that means what you are to prove now. The finally what you are to prove is that your j is equal to summation I am taking as in one term I vary from 1 to infinity, and these two terms I am going to collect as greatest integer n upon p raised to the power I minus greatest integer n minus 1 upon p raised to the power I. This finally we are to prove. If we can prove this, then the theorem will automatically be proved. So finally we are to prove this result now. And how to prove this? Let us see. This I vary from 1 to infinity. There can be two possibilities. Actually, what we are to prove that this term, let us close the bracket. I will actually prove that this particular term, that box n upon p power I minus box n minus 1 upon p power I, this term is equal to 1 whenever p power I divides n, and it is 0 whenever p power I does not divide n. So what we will prove, rubbing the board now. This result I am not going to rub because actually we want to prove this result now. If we can prove this result, that means we have proved the theorem. Okay, so for that I am claiming that this term n upon p power I box minus n minus 1 upon p power I box greatest integer function means is equal to 1 if your p power I divides n, and 0 if p power I does not divide n. This I will prove now. And this can be proved definitely in step by step. First I'll take when pi divides n, I'll prove that this is equal to 1. Then I'll take that if pi does not divide n, and I'll prove that this is equal to 0. So case 1. Case 1. If your p power I divides n, then definitely there exists some integer q such that n is equal to pi into q. Can we write like this? So substitute this value here. So substituting this value here, this term, suppose this is a. Suppose this is a. What your a becomes? It becomes greatest integer. You are substituting the value of n here, piq, p power I into q divided by p power I, minus, you will get here p power I q minus 1 upon p raised to the power I, greatest integer, and it is equal to, here pi will be cancelled, you will get greatest integer of q minus, here separating the two terms you will get q minus 1 upon p raised to the power I. Now q is an integer. Q is an integer. For any integer, its integral part is the integer itself and the fractional part is 0. So box of q will become equal to q minus. What about this? This is some integer minus something positive, and that lies between 0 and 1. So if suppose it is 10, then 10 minus something fraction is 9 point something. So 9 point something, box is 9. So if it is 10, the result is coming to be 9. If it is q, the result will be q minus 1. Q minus 1. And solving it, q minus q plus 1, you will get equal to 1. That means whenever pi divides n, this expression is going to be equal to 1. The first part we have proved. Now move on to the second part. Move on to the second case. Second case, when pi does not divide n. So case 2. Case 2 means pi does not divide n. So if pi does not divide n, dividing n by pi, we will have some quotient q and definitely some remainder which will be strictly greater than 0 and will be less than p raised to the power I. Because if it is 0, the division is complete, but the division is not complete, so this remainder must be not non-zero. And your n will become this case, and your n will be equal to pi into q plus r, p power I q plus r, where r lies between 0 and pi. Now substitute this value of n here. So what the expression a will be now? The expression a will become p raised to the power I q plus r over p raised to the power I minus, here you will get p raised to the power I q plus r minus 1 upon p raised to the power I, and separating you will get q plus r upon p power I plus, minus, here you will get q plus r minus 1 upon p power I. Now q is an integer and this r upon p power I is a fraction, is a number lying between 0 and 1 because of this. This r upon p power I is something less than 1 but is greater than 0, so it is fraction. So some integer plus fraction. Its greatest integer will be the integral part and the integral part is q. So you will get q here minus. Once again, this r minus 1, since r is greater than 0, r minus 1 may be at least 0, may be equal to 0, otherwise it is something fraction. So 0 or fraction, some integer plus 0 or fraction. Once again, the greatest integer part will be q. So it is q minus q equal to 0. That means we have proved that this is equal to 0 whenever p power I does not divide n. Now move on to this result. I'm rubbing this case now. look at this result now. Look at this result now. We know that Pj max divides n. That means Pj plus 1 does not divide n. You can see it as P power 1 divides n, P power 2 divides n, P power 3 divides n, and so on. P power j divides n, but P power j plus 1 does not divide n. Now look at this summation. In this summation, you put I is equal to 1. I is equal to 1, so you will get P. And P divides n. P divides n. So this term will become equal to 1. If you put 2, P square divides n, so again it will be 1. You put 3, once again it divides n, so you will get 1, and so on up to P power j, because P power j divides n. You will once again get 1. So how many 1 are there? This is 1 for this P power 1, this is for P square, this is for P cube, and this one is for Pj. So these are total j ones. So j terms are here. And after that Pj plus 1. Now Pj plus 1 does not divide by n. So this term will become 0. And afterwards every term will become 0. So 1 plus 1 j times you will get equal to j. So this sum is equal to j, and that is what we wanted to prove. That is what we wanted to prove. This is j. And hence we have proved the de Polignac formula. And you have seen an application of de Polignac formula as well. Now, two more different type of problems of de Polignac formula I am going to take. Earlier I have taken the problem where 7 was a prime number. Suppose it is not a prime number. Suppose you have to see how many powers of 16 say. So the 16 max divides 200 factorial. 16 power I. So what is the value of I? So better if you break this 16 into some prime number. If it is some power of prime, then it is better. So it is 2 power 4. So you write it as 2 power 4i max divides 200 factorial. And now this 4i is equal to 200 upon 2 box plus 200 upon 2 square box plus 200 upon 2 cube box plus and so on. So what you are going to get is I is equal to 1 upon 4. I have taken this 4 to the other side. And now this is 100 plus 50 plus 25 plus 12 plus 6 plus 3 plus 1, and rest all will become 0. So what is your I now? Once again, if it is not completely divisible, you will have to take the integral part. This is 150, 175, 187, 193, 196, 197. So you will have to take the greatest integer part. It is 197 upon 4 and then box. So what it is equal to I think it is 49. I think it is 49. Yes, it is 49. So I is 49. So maximum 49 powers of 16 will divide 200 factorial. Okay. In one of the problems I have taken prime numbers. Here I have taken prime power. It may not be a prime. It may not be a prime power. It may be a simple number, product of two primes. Suppose you want to find 6 raised to the power I max divides 100 factorial. What is the value of I? Now this 6 can be broken into factorials of factors 2 and 3. So you take how many? 2 raised to the power I max divides 200 factorial. What is 3 power I max divides 200 factorial? And then take their minimum. So how to do that? For 2, you will get, suppose here I am taking j. So I is equal to 200 upon 2 greatest integer plus 200 upon 2 square greatest integer plus and so on. And similarly j is 200 upon 3 greatest integer plus 200 upon 3 square greatest integer plus and so on. So what the values we are going to get here is, first case is 100 plus 50 plus 25 plus 12 plus 6 plus 3 plus 1, that means 197. In the second case you will get, dividing it, 66 plus 22 plus 7 plus 2 plus rest of the terms will become 0. So it is 88 plus 9, so 97. Out of these two, 197 and 97, what is minimum? The minimum is 97. So that means maximum 97 powers of 6 will divide 100 factorial. That means 6 raised to the power 97 max divides 100 factorial. I have taken here 200, sorry. So change the question, make it here 200 factorial. I have taken 200. So it is 6 raised to the power 97 max divides 200 factorial. Suppose it is not 6, it is 18 here. And 18 means 2 into 3 square. 2 into 3 square. So what to do? You are to do the same way. For 2 you have 197, for 3 you have 97, 3 square. So take 97 upon 2 greatest integer once again. And now it comes 48. And now you are, instead of taking minimum of these two, take minimum of these two. And minimum of these two is 48. So that means 18 raised to the power 48 max divides this 200 factorial. Okay. Suppose it is not 18, it is 72. And 72 means 3 square into 2 cube. So here 3 square we have divided by 2 and we have taken the greatest integer part. For 2 cube, the result for 2 is 197. Once again, divide 197 by 3 and take greatest integer function. So what you are going to get is 65. And now you are to take minimum of these two. And minimum of these two is once again 48. So 72 raised to the power 48 max divides 200 factorial. So with this theorem and with these results and with these questions, I am going to end this chapter of arithmetic functions here. And in the next video, I will introduce the new chapter, that is quadratic residues. Till then, thank you. Thank you once again.